LEDs don't get their color from their plastic covers. You can see that with a transparent LED that glows the same red color. The light comes from the electronics themselves. The casing just helps us tell different LEDs apart. In 1962, General Electric engineer Nick Holonyak created the first visible LED glowing a faint red. A few years later, engineers at Monsanto created green LED. But for decades, those were the only two colors available, limiting LEDs to indicators, calculators, and watches. The missing piece was blue. If scientists created a blue LED, they could mix red, green, and blue to make white light and every other color. This would unlock LEDs for every type of lighting in the world, from light bulbs to phones, computers, TVs, and billboards. But blue proved almost impossible to make. Throughout the 1960s, every major electronics company, IBM, GE, Bell Labs, raced to create the blue LED. They knew it would be worth billions. Despite thousands of researchers and massive investments, nothing worked. 10 years turned into 20, then 30. The hope of using LEDs for general lighting faded away. A Monsanto director predicted LEDs would never replace kitchen lights, only being useful for appliances and car dashboards. This might still be true today, if not for one engineer who defied the entire industry and made 3 radical breakthroughs to create the world's first blue LED. Shuji Nakamura was a researcher at Nikkei, a small Japanese chemical company that had recently expanded into semiconductor production for red and green LEDs. By the late 1980s, the semiconductor division was failing. They were competing against far more established companies and losing badly. Tensions ran high. Younger employees begged Nakamura to create new products while senior workers called his research a waste of money. Money was in short supply at Nikkei. Nakamura's lab consisted mainly of machinery he had scavenged and welded together himself. Phosphorus leaks created so many explosions that co-workers stopped checking on him. By 1988, supervisors told Nakamura to quit. Out of desperation, he brought a radical proposal to company founder and president Nobuo Ogawa. What if Nikkei could create the elusive blue LED that Sony, Toshiba, and Panasonic had all failed to achieve? After suffering loss after loss for more than a decade, Ogawa took a gamble. He devoted 500 million yen, about $3 million, likely around 15% of the company's annual profit, to Nakamura's moonshot project. Everyone knew LEDs had potential to replace light bulbs because traditional bulbs are terrible at making light. They work by running current through a tungsten filament that gets so hot it glows. But most of the electromagnetic radiation comes out as infrared heat. Only a negligible fraction is visible light. In contrast, LED stands for light-emitting diode. LEDs primarily create light, making them far more efficient. When you have an isolated atom, each electron occupies a discrete energy level, like individual seats in a hockey stadium. All atoms of the same element, when far apart, have identical available energy levels. But when you bring multiple atoms together to form a solid, something interesting happens. The outermost electrons feel the pull not only of their own nucleus, but of all the other nuclei as well. Their energy levels shift, becoming a series of closely spaced but separate energy levels, an energy band. The highest energy band with electrons is the valence band. The next higher energy band is the conduction band, like the balcony level. In conductors, the valence band is only partially filled. With a little thermal energy, electrons can jump into nearby unfilled seats. When an electric field is applied, they can jump from one seat to the next, conducting current through the material. In insulators, the valence band is full, and the band gap, the energy difference between valence and conduction bands, is large. When an electric field is applied, no electrons can move. There are no available seats in the valence band, and the band gap is too big to jump to the conduction band. Semiconductors are similar to insulators, except the band gap is much smaller. At room temperature, a few electrons have sufficient energy to jump into the conduction band, where they can easily access nearby empty seats and conduct current. The empty seats they leave behind in the valence band can also move. Really, it's nearby electrons jumping into those empty seats. From afar, it looks like the empty seat or hole is moving like a positive charge in the opposite direction to the electrons. Pure semiconductors aren't that useful by themselves. To make them functional, you add impurity atoms into the lattice, a process called doping. For example, in silicon, you can add phosphorus atoms. Phosphorus is similar to silicon and fits easily into the lattice, but brings one extra valence electron. This electron exists in a donor level just beneath the conduction band. With a bit of thermal energy, all these electrons can jump into the conduction band and conduct current. Since most of the mobile charges are electrons negative, this is called N-type semiconductor. There's also P-type semiconductor, where most mobile charge carriers are positive. To make P-type silicon, you add atoms like boron, which has one fewer valence electron than silicon. This creates an empty acceptor level just above the valence band. Electrons can jump out of the valence band, leaving behind positive holes that carry current. The material overall is uncharged. It's just that most mobile charge carriers are positive holes. Things get interesting when you put p-type and n-type semiconductors together. Without even connecting to a circuit, some electrons diffuse from n to p and fall into holes in the p-type. This makes the p-type slightly negatively charged and the n-type slightly positively charged, creating an electric field inside an inert piece of material. Electrons keep diffusing until the electric field becomes so large it prevents them from crossing over. This establishes the depletion region, an area depleted of mobile charge carriers with no electrons in the conduction band and no holes in the valence band. If you connect a battery the wrong way, it simply expands the depletion region until its electric field perfectly opposes the battery and no current flows. But if you flip the battery's polarity, the depletion region shrinks, the electric field decreases, and electrons can flow from N to P. When an electron falls from the conduction band into a hole in the valence band, that band gap energy is emitted as a photon. The energy change of the electron is emitted as light. This is how a light-emitting diode works. The size of the band gap determines the color of light emitted. In pure silicon, the band gap is only 1.1 electron volts. So the photon released is infrared. These LEDs are actually used in TV remote controls and can be captured on camera. Moving up the spectrum, you can see why the first visible LEDs were red, then green, and why blue is so hard. A photon of blue light requires more energy and therefore a larger band gap. By the 1980s, after hundreds of millions of dollars spent hunting for the right material, every electronics company had come up empty-handed. But researchers had figured out the first critical requirement, high-quality crystal. No matter what material was used for the blue LED, it required a near-perfect crystal structure. Any defects in the crystal lattice disrupt electron flow. Instead of emitting energy as visible light, it dissipates as heat. The first step in Nakamura's proposal was to disappear to Florida. He knew an old colleague whose lab was using a new crystal-making technology called metal organic chemical vapor deposition MOCVD. An MOCVD reactor, essentially a giant oven, was and still is the best way to mass-produce crystal. It works by injecting vapor molecules of your crystal into a hot chamber where they react with a base material called a substrate to form layers. It's crucial that the substrate lattice matches the crystal lattice being built on top to create a stable, smooth crystal. This is a precise art. Crystal layers often need to be as thin as just a couple of atoms. Nakamura joined the lab for a year to master MOCVD, but his time there was miserable. He wasn't allowed to use the working MOCVD, so he spent 10 of his 12 months assembling a new system almost from scratch. Even worse, his lab mates shunned him because Nakamura didn't have a doctorate or any academic papers to his name. Nietzsche didn't allow publishing. His lab mates, all PhD researchers, dismissed him as a lowly technician. This experience fueled him. Nakamura wrote, "I feel resentful when people look down on me. I develop more fighting spirit. I would not allow myself to be beaten by such people." Choosing the right material. Nakamura returned to Japan in 1989 with two things: an order for a brand new MOCVD reactor from Nietzsche, and a fervent desire to get his PhD. At that time in Japan, you could earn a PhD without university by simply publishing 5 papers. Nakamura had always known his chances of inventing the blue LED were low, but now he had a backup plan. Even if he didn't succeed, he could at least get his PhD. With MOCVD mastery under his belt, the question was, which material should he research? Scientists had narrowed options to 2 main candidates, zinc selenide and gallium nitride. Both were semiconductors with band gaps theoretically in the blue light range. Zinc selenide was far more promising. When grown in an MOCVD reactor, it had only a 0.3% lattice mismatch with its substrate gallium arsenide. Therefore, zinc selenide crystal had about 1,000 defects per square centimeter, within the upper limit for LED functioning. Its only issue, while scientists had figured out multiple ways to create N-type zinc selenide, no one knew how to create P-type. In contrast, gallium nitride had been abandoned by almost everybody for 3 reasons. Much harder to make high-quality crystal. The best substrate for growing gallium nitride was sapphire, but its lattice mismatch was 16%, resulting in over 10 billion defects per square centimeter. P-type was elusive. Like zinc selenide, scientists had only created N-type gallium nitride using silicon. Power output requirements seemed impossible. To be commercially viable, a blue LED would need at least 1,000 microwatts of light output power, 2 orders of magnitude more than any prototype had achieved. Between the 2 candidates, almost all researchers focused on zinc selenide. Nakamura surveyed the crowded field and decided that if he were going to publish 5 papers by himself, he'd better focus on gallium nitride, where competition was much less fierce. This material's main claim to fame was one development back in 1972 when RCA engineer Herbert Maruska made a tiny gallium nitride blue LED, but it was dim and inefficient. RCA slashed the project's budget, calling it a dead end. 20 years later, scientific opinion hadn't changed. When Nakamura attended Japan's biggest applied physics conference, talks on zinc selenide had over 500 attendees. Talks on gallium nitride had 5. Two of those 5 attendees were the world experts on gallium nitride, Dr. Isamu Akasaki and his former grad student, Dr. Hiroshi Amano. In contrast to Nakamura's background, they were researchers at Nagoya University, one of Japan's best. A few years earlier, they had made a breakthrough on the high-quality crystal problem. Instead of growing gallium nitride directly on sapphire, they first grew a buffer layer of aluminum nitride. This has a lattice spacing between the other two materials, making it easier to grow a clean gallium nitride crystal on top. The only issue, aluminum caused problems for the MOCVD reactor, making the process hard to scale. Back at Nitya, Nakamura couldn't get gallium nitride to even grow normally in his new MOCVD reactor. After 6 months, desperate for results, he decided to take the machine apart and build a better version himself. His 10 months assembling the reactor in Florida suddenly became invaluable. He began a relentless routine. Arrive at 7 a.m. Spend the first half of the day welding, cutting, and rewiring the reactor. Spend the rest of the day experimenting with the modified reactor. Go home at 7 p.m., eat dinner, wash, and sleep. Nakamura repeated this routine every single day, taking no weekends and no holidays except New Year's Day, the most important holiday in Japan. After a year and a half of continuous work, he came into the lab on a winter day in late 1990. As usual, he tinkered in the morning, grew a gallium nitride sample in the afternoon, and tested it. This time, the electron mobility was 4 times higher than any gallium nitride ever grown directly on sapphire. Nakamura called it the most exciting day of his life. His trick, adding a second nozzle to the MOCVD reactor. The gallium nitride reactant gases had been rising in the hot chamber, mixing in the air to form powdery waste. But the second nozzle released a downward stream of inert gas, pinning the first flow to the substrate to form a uniform crystal. For years, scientists had avoided adding a second stream to MOCVD because they thought it would introduce more turbulence. But Nakamura used a special nozzle so that even when streams combine, they remain laminar. He called his invention the two-flow reactor. Now, he was ready to take on Akasaki and Amano in the race for the blue LED,